in the last part of Unit 5, we were discussing error detecting and correcting codes. And in the session previous to your test, we started off with one class of error correcting codes, which was block codes, under which we started off with the generation of and generation and detection of linear block codes. This was one of the simplest type that was possible. Okay, so let's look for another flavor of these linear block codes, which is known as cyclic codes. Okay, these are again one class of linear block codes. Unlike the first class that we had seen earlier, we tried to build generator matrix based on the given information of n and k. In fact, just k was enough to generate and detect the error correcting codes. So it is relatively easy for constructing generator matrix for single error correcting codes, which were also called as Hamming codes. Okay, so it's easy to yeah, it's, as I said, it's very easy to build generator matrix where we call it as G, or simply G in the bold letter. So it's easy to build G generator matrix for linear block codes, or I can say for Hamming codes, okay, which are single error correcting codes. But as you try to detect and correct more number of bits, more number of error bits in the received code, the procedure for generating the generator matrix would become a little complex. Okay, so it's not so easy to construct higher order error correcting codes, in other words. Okay, so cyclic codes, on other hand, they come with two important properties, or two important features with which it's the job of generating or building a generator matrix, it becomes easy. So one important property of cyclic codes being they are mathematically have a nice structure. Okay, so they have nice mathematical structure. Okay, although we begin with not so good when we try to explain, it seems that they are not so good in mathematically structure, but we can have systematic cyclic codes where they give good properties with respect to their structure. Right? So that permits the design of higher order correcting codes. Okay, so this implies building higher order error correcting codes. Okay, fine. So next important feature, or the attractive feature of cyclic codes being encoding and syndrome calculations that we have done even in case of Hamming codes can easily be implemented in cyclic codes. But the cyclic codes use simple shift registers, arithmetic shift registers, to implement encoding and syndrome calculations. Okay, say encoding and syndrome calculations can easily be implemented, is easy to implement, which uses, as I said, which uses simple shift registers. Okay, we will see that. Probably you have done one of the experiments as 10th experiment in your CS1 lab as well. Probably you have a fair idea, but we'll try to understand the mathematical background of generating cyclic codes. Okay, all right, so let's try to understand the structure first. As we told, it's easy. I mean, it has got simpler mathematical structure. We'll try to understand that. as a first part of the cyclic codes, and then try to encode and try to decode using syndrome calculations for specific cases. Okay. So in cyclic codes, the code words are simple, as the name itself says, that it's cyclically shifts of one of each other. Okay, so as I said, if, okay, the mathematical structure, I can say. The mathematical structure of cyclic codes is simpler, where if I say a code, say C, we denoted it as bold C, or you can say this as a row vector C. If it is represented as C1, C2 up to Cn minus 1, okay, as a code word, okay, let us represent this as a code word, then the word cyclic code refers that the set C2, C3 up to Cn comma C1, which is obtained as one left shift of the previous code word. Similarly, C3, C4, Cn, C1, C2 are also code words, okay, which are obtained by cyclically shifting. In fact, we have done a left shift here, so we have obtained a few set of code words which can also be part of the cyclic code. Okay, so we can, in general, we can write that if in general there are n code words, will have n tuple. It's not n tuple. I'm sorry, one second, there is a problem with, yeah, it's a code word. As I said, it's a block code. Block code is n comma k code word. It's represented as n comma k, where n is the length of the bits in the code word and k is the number of bits in the message word, and hence it should have been cn minus 1 comma cn. I missed that term. Okay, I think that's clear now. In general, I can write, if a code word is represented as, in general, if a code word is represented as, okay, in general, this is represented as, say, C as n tuple, C1, C2, which you have done already. It's an n tuple code word, is a code vector, I can say, say of some code C. Then C of I, okay, where I represents the number of shifts that has happened in the code word tuple, which is represented as Ci plus 1, Ci plus 2. Like here, the earlier case, one shift got me C2 as its subscript. So ith would have the first element as I plus 1, and it will go on up to Ci plus 2, and somewhere in between you will have Cn, and obviously after cyclic shift you will have C1, C2, and up to Ci somewhere here. Okay, this denotes it's a cyclically shifted by I places to the left. Okay, this represents, okay, denotes, I can say that C shifted cyclically I places, okay, to be specific, to the left. Okay, then cyclic codes can be described in a neat polynomial form. The cyclic codes in polynomial form, this actually makes their structure mathematically simpler. because of this nature. Okay, so this property of cyclic codes is extremely useful in the analysis and implementation of these codes. Okay, so the vector C, as I have denoted with the tuple, the vector C, which is from C1 to Cn, can be mathematically represented in polynomial form as C of x, okay, x, where C1 is the first bit in the code word, times x n minus 1 plus C2 x n minus 2. When we take specific cases, it will be more clear, but we'll have to understand the structure of the cyclic code in the first place, where n denotes, I mean, where n is number of bits in the code word. Okay, in the code word. Therefore, this is a polynomial of order n minus 1. Okay, so this will have its, therefore C of x is an n minus 1 degree polynomial. Okay, the coefficients ci's, okay, the coefficients ci, c1 to cn, are obviously either 0 or 1. The ci's are either 0 or 1. And also these follow the properties of modulo 2 addition, very exactly similar to the earlier Hamming codes. Okay, and obey, I can say, and obey modulo 2 addition and subtraction. Okay, and this seems to be that there would be multiplications as well, as I am multiplying with c1 to some of variable as x. So even the multiplication of binary digits will obey the similar law, where your 0 times 0 is 0, and unlike unless and until where both bits are 1, the product would be 1. It's a simple basic mathematical rule. But the addition and subtraction will be obeying your modulo 2 rule. Okay, such that the code polynomial in general, therefore the code polynomial of C of I of x, where I C of C superscript I represents ith times cyclically shifted towards left. Okay, so for the vector of cyclically shifted vector C of I can be written as C of I of x, which will be equal to, as I have told, the ith cyclically shifted, I mean ith by ith position, will have the coefficient ci plus 1, ci plus 2, and running up to ci, and hence this can be represented as ci plus 1 x n minus 1 plus ci plus 2 x n minus 2, because we know that the original code has of the degree of n minus 1. Obviously cyclically shifted version should also have the degree of n minus 1, because we are not multiplying with any other quantity at this point. So this is cn xi plus c1 xi minus 1 up to ci into x bar 0. Okay, so that would be the structure in general of the polynomial representation of the code word and the cyclically shifted code word. Okay, so with this we can draw one of the important and interesting properties of code polynomials is that, as you can see, okay, an important feature or the property which will help us in generating or building generator matrix an important property, okay, of code polynomials is that when x power I c of x is divided by, we'll see this, when I multiply the c of x, the original code word, by x power I, then then if I divide by a polynomial x power n plus 1, then the remainder is, we'll see what would be the remainder. Okay, this could be the one of the important properties going ahead. Let me check what will happen if I try multiplying with x power I. I know that c of x is represented as, we know that c of x is represented as c1 xn minus 1, c2 xn minus 2, and up to cn. I multiply with x power I. So x power I c of x would give me, I'll try to multiply with simply as x c of x. Then I'll try to apply your induction rule. So I'll take I as 1 first. So for I is equal to 1, I would obtain x times c of x. So this will be c1 x power n plus c2 x power n minus 1, so on up to cn x. Then divide by x power n plus 1. You know the division of the polynomial, okay, which is, okay, the dividend is c1 x power n, c2 x power n minus 1 up to cnx, and I'm dividing by x power n plus 1. Okay, so the first element in the quotient is c1, so this would be c1 x power n, okay, plus, okay, c1 x power n plus c1, okay, plus c1. And how to subtract these two? If I subtract these two elements, I would get c1 x power n, c1 x power n, subtraction will cancel with each other, and obtain c2 x n minus 1 plus, that could be a second term with c3 x n minus 2, and up to cnx minus of cn. As I told, the addition and subtraction in case of binary would result in the same quantity, so that this I can write it as plus c1. If you carefully observe, by dividing x power n plus, by dividing the code polynomial which was multiplied with x with order of I as 1, then divide by x power n plus 1, where n is the nth order of a polynomial, I would get a similar code word which is exactly 1 times left shifted version of the original code word, right, where x power n minus 1 is multiplied with the coefficient c2, and with the decreasing order of the degree in the polynomial, I would get all other coefficients in the original code word. Okay, so and hence I can say that if I divide the code word, if I continue for the value I is equal to 2 and up to I is equal to n in general, using induction method, I can write in general the remainder for this division would result in just the ith shifted of the original code word, which I can write this as c of I of x. Okay, so this would be one of the important property of the code word moving ahead. Okay, all right, so this had to be noted down carefully, that which is useful for us later. Okay, we let's now introduce the concept of generator polynomial. So far we are just discussing about the code polynomial, we need to find out what is a generator polynomial and try to take the input messages and try to encode the input messages using this generator polynomial. That's what we had done in case of Hamming codes as well. Okay, so now let's try to define the generator polynomial. Okay, we call it as code generator polynomial, which we will represent it as g of x, because it's everything is in here moving forward will be in terms of just linear equations. Okay, since each n comma k code word can be represented, okay, since each, remember still it is a block code which can be represented as n comma k code word can be represented as, we have written this several times so far now, represented as c of x, c1 x power n minus 1, c2 x power n minus 2 up to cn. G of x is a generator polynomial of degree k minus n. The generator polynomial g of x is of degree n minus k, where this represents the redundancy involved in the encoded word. Okay, if for say a data polynomial, because finally we result in a code word by taking the product of data polynomial and generator polynomial, and hence you can say that if for data polynomial d of x, let's represent the data polynomial also as in a mathematical structure. So finally the generator polynomial should be of order n minus k, and we know that the code word is of the order n minus 1, and obviously the data polynomial would be of the order k minus 1, where this is d1 x k minus 1 plus d2 x k minus 2 up to dk. Okay, this implies the generator polynomial g of x would be simply the product of d of x and c of x. Okay, so you should note that there are 2 power k distinct data polynomials or code words that are possible. Okay, so, but for a cyclic code, a code word after cyclic shift is still a code word. Okay, so that should be noted as well. Okay, all right, so we have just one last property, or in terms of theorem, with which we are ready to do one one example such that it will be all these in general mathematical equations will be more clear. Okay, that theorem is known as cyclic linear block code theorem. Okay, so this theorem states that if g of x is a polynomial, if this is a polynomial of degree n minus k, okay, and is a factor of x power n plus 1, of course this is modulo 2, it follows modulo 2 rule, then g of x is a generator polynomial Okay, I'll make this more clear, is a generator polynomial that generates, okay, that generates your n comma k linear cyclic block code. Okay, we'll try to prove this first, then we take a specific case. Okay, I repeat this statement. G of x, as we have seen earlier, it's a polynomial which can be represented as a polynomial of degree n minus k, which is obtained by the product of multiplying the code word with the input data word. The code word had a polynomial of n minus 1, and the data word has a polynomial of order or degree k minus 1, and hence their product will be obviously of degree n minus k. And if this g of x is a polynomial which is a factor of x per n plus 1, in the sense, if we can factorize x per n plus 1 into several polynomials, one of those factors would be g of x, and that we call it as a generator polynomial, and that definitely generates an n comma k linear cyclic block code. Okay, so that is the explanation of the theorem. Let us try to prove this before we move on to one example. Okay, say for a data vector, that we have seen as d1, d2 up to dk, okay, the data polynomial that we represented in form of polynomial is d of x d1 x bar k minus 1 plus d2 x bar k minus 2 up to dk. Okay, let's consider few polynomials, few k polynomials in this fashion, where the first polynomial, let us represent this as g of x. Let us say another polynomial which is obtained by multiplying with x, and we can keep on multiplying with x, and we can go up to k minus 1 g of x. We have a degree of each of these polynomials. Let's consider these polynomials of degree, okay, each having a degree of say n minus k. Let this be n minus k plus 1. This could be n minus k minus of k minus 1, which is your n minus 1 respectively. Okay, hence if we take linear combinations of all these, this implies the linear combinations of these polynomials. I try to take linear combinations, which I take d1 times xk x bar k minus 1 times g of x. Okay, so this would be the linear combination of the data vector. So these are the polynomials which are defined in this fashion, and if I try to take the linear combination with respect to the data vector, I would obtain the next term in the data polynomial is d2 times x bar k minus 2 times xg of x, right? So which would give me d2 times xk minus 2 times g of x, and up to, say, if I can go up to dk times g of x. I've just taken the linear combination with respect to g of x. Then this would be obviously the polynomial d of x times g of x. That's what I have done. I've just taken the linear combination of the data vector with respect to the polynomial g of x of the order n minus k. Okay, so irrespective of the values of these di's, the product d of x, g of x, what would be the degree of this product? This would have the degree of this will have the degree, because g of x has a degree of n minus k. So highest order, this would be k minus 1 plus n minus k. This would give me the degree of n minus 1. So irrespective of, so carefully noting that fact, where irrespective of the values of these di's, okay, the order of d of x times g of x will be definitely less than or equal to n minus 1. Okay, so hence a code word, obviously we know that a code word will have the order of n minus 1. So the resultant of the product of this polynomial d of x times g of x has resulted in another polynomial of the order n minus 1, and hence we can say that this could be one of the code words in our code set. Okay, so this implies, I can say that hence a code word is formed. Okay, note that there are a total 2 power k combinations of this data polynomial, or d of x polynomial. Okay, so which correspond to 2 power k data vectors. Okay, so if you take all such combinations, say this is just one combination d1 d2 up to dk, I can go up to 2 power k combinations of this data vector, and hence I can generate several polynomials with the product of d of x and g of x that will consume 2 power k code words of the order n minus 1. Okay, so this implies, okay, for considering all 2 power k combinations of data vector d of x, we would generate a linear n comma k code. Okay, this is linear code, that's fine, because you have taken linear combinations of the generator polynomial g of x and the data vector which is d of x. But how to prove that this is a cyclic? Yes, please.
So for the message, d of x will be unique for a given message, right? So g of x would be changing.
Exactly.
There will be different number of g of
G of
x.
x would be, yeah, there would be definitely different types of g of x depending on d of x. That's perfectly right, because
No, so d
depending
of
on d
x will
of
be
x, you will have,
d of x will be fixed for a given message segment, right? Data
okay,
vector. G of x can
right,
be multiple of them. Based on that,
yeah,
multiple code words can be produced for a given d of x.
given data set. That's right. There could be different answers for, I mean, if you take different g of x as a polynomials. That's perfectly right.
And then,
Okay, okay.
is there any
I'll take,
specific method of finding? Yes, yes.
yeah, I'll try to address that. We'll take an example where that would give you two g of x polynomials that are both are possible. Okay,
Yes.
I will address that. Don't worry. Okay. All right. So this seems to be, as you know, rightly, you asked, g of x, as we have just generalizing the things here. There is no systematic method of obtaining g of x. Okay, which would lead to ambiguity. So definitely this is a kind of a non-systematic way of finding out the code word, where we can modify this method and try to obtain a cyclic code in a more systematic way. That would be the other half of the cyclic code part. Okay, you don't worry about that. That first try to address the mathematical aspects behind the cyclic codes. Okay, so I was talking about right, so this is fine with the linear block code, since we are talking about linear block code as one of the flavors in this course. But since it's a cyclic codes, how do we prove that this is cyclic code as well? So to prove that this code is cyclic, let us consider to prove that this code is cyclic. Okay, let us define C of x as a code word as C1 x per n minus 1, C2 x per n minus 2 up to Cn. Okay, be a polynomial in this code. Then we have done this. Then x times C of x, if I try to multiply with x, what would be this would result in? This would be C1 times x power n plus C2 times x power n minus 1, and so on up to Cn times x. Okay, what I'll try to do, little mathematical adjustment here based on the modulo 2 addition. I will try to add C1 twice. Okay, so we know that bit addition of 0 would result in 0. Additions of ones in binary or in modulo 2 additions, this also result in 0. So C1 plus C1 will not affect anything in the polynomial in the equation original, but this will prove me something where I'll take C1 to one term and I'll say that I'll try to combine these two terms. Okay, to be more specific, I'll pick this first term and one C1, and I'll try to write this as, which is C1 is common, x power n plus 1, plus I'll take C1 in the other term, which comprises of C2 up to Cn, and this would give me a polynomial C2 x power n minus 1, and there could be another term C3 x power n minus 2 and up to Cnx plus C1, which has been extra. Carefully note that this is C1 times x power n plus 1 plus, sorry, this is x power n plus 1 plus if you carefully look at this, this is of the this is a polynomial of degree n minus 1, and but the coefficients are cyclically shifted of the original code polynomial, and I can represent this as, this is original code word C, but with one left shifted version of the original code word. Okay, this is how I can represent the resulted code word when I multiply with x. Since we have assumed that, if I check back the original assumption, since I have assumed that g of x is a polynomial of degree n minus k and is a factor of x power n plus 1. Okay, and is a factor of x power n plus 1. So with that initial assumption, I can say that because of the fact that x c of x is nothing but, since c of x we have defined it as product of d of x and g of x, right? So this is a code polynomial which is resulted by linear combinations of g of x. So this is a code word that we have generated, and hence x c of x is nothing but x times d of x times g of x. Okay, and g of x is a factor of the polynomial x power n plus 1. Okay, so this is the basic assumption. The second half of this is basic assumption. The first half is that we have proved that this is the linear combination of the generator polynomial g of x. So with considering both of these facts, this implies that, okay, c of of 1, which is on the right hand side, the left hand side is which is x times d of x g of x, and also g of x is a factor of x power n plus 1, which is the first term which we have obtained as c1 times x power n plus 1. This implies that the second term in the on the right hand side must also be a multiple of g of x, right? The first term is obviously where x of n power plus 1 is a factor, where g of x is a factor of x power n plus 1, and the right hand side must also be similarly should also be a multiple of g of x, and hence the cyclically shifted code word, the one position left shifted version of the original code word, has resulted as the linear combination of g of x. Okay, so this implies that c of 1 can also be expressed as multiple of g of x, which could be g of x times d of x, okay, for some vector d. Okay, so therefore c of 1 is also a code polynomial. Okay. This proves that this is a linear code, and also it is a cyclic code where the codes are obtained by cyclically shifting the original code word. So this is just a case with multiplying with x. You can do by induction. You can say that therefore by induction, okay, we can prove that the linear n comma k code generated by d of x times g of x is cyclic. Okay, let's quickly take one example, as I was trying to stress that by taking a specific case we can understand in a more better way. Okay, so very basic example. Okay, so let's try to build a generator polynomial for a specific cyclic code. Okay, I can say that let us build g of x for a 7 comma 4. I'll take n comma k as 7 and as 7 and k as 4 cyclic code. Okay, and let's also find code vectors, and also let's find the code vectors that we had done similarly for linear block code. Okay, I can say simply Codewords. Okay, so in this case, how to find this out? So in this case, n is 7, k is 4, right? So that this implies n minus k is 3. Okay, that implies that what is the implication of that? We have seen that the generator polynomial is of the degree n minus k. Yeah, so the generator polynomial g of x is of the order n minus k. That's the reason we should know what is the order or what is the highest degree of the generator polynomial. Okay, so this therefore g of x is of the order n minus k, which is 3. Okay, so we know that this generator polynomial g of x, we should have the factor of x power n plus 1, in the sense g of x, in the sense x power n plus 1 in our case. I'll write that sentence, since g of x is a factor of x power n plus 1, which is in our case is x power 7 plus 1. Okay, so therefore x power 7 plus 1, when you try to factorize this, one of that should be g of x. Okay, so we can try to find out the factors of x power 7 plus 1, keeping in the mind that g of x is of the order 3. Okay, so with that I can say some polynomial multiplied with multiplied with the generator polynomial should give you x power 7 plus 1. So one of that would be x power 3 plus, say, since generator polynomial should be of the order 3, so I should take the highest order highest degree of the polynomial as 3. So x power 3, x power 2 plus, I cannot take x because multiplying with another polynomial should result in a factor 1 as well, and hence this forces me to take plus 1. Okay, I hope you get that point. Okay, so if I try to multiply with another polynomial, the multiplication with that of x power 3 plus x square plus something should also result in x power 7 plus 1. Okay, so similarly I can also take another a similar polynomial of the degree x power 3. This could be x power 3 plus x plus 1. If you carefully look at this, and if I try to multiply these two polynomials, the remaining polynomial is simply x plus 1. So x power 7 plus 1 can be factorized into three polynomials, where the two polynomials of the order 3 are generated, and I can pick either of these g. So this could be my g, or this could be my g of x. So there are two solutions to this problem, and hence, as you are rightly saying, that there could be two encoding tables. Okay, so this implies that this is a case with this is a case with two options to choose.
So by factor, you mean there should be no
Yes,
remainder,
please go
right?
ahead.
By factor, there should be no remainder.
Exactly, exactly. Let's say,
I think this polynomial will give
yes,
a
that's right.
remainder.
No, no, not a remainder. In a sense, should be divisible by that. It should be divisible.
If
In a
it,
sense, factor in the sense, yeah, it's common factors. X power 7 plus 1 has a factor which can be represented like something like this. Say 18 can be factorized into say 2 into 3 into 3, something like that, where 2 and 3 are the factors of the number 18. Okay, so that means that this x power 7 plus 1 can be disintegrated into a product of three different polynomials.
so that 18 should be divisible by 2, 3, and 3 also.
Yeah,
So
if you divide this to if you divide by this, what will the remainder is as I told you, the property, the theorem, as I told you, when you try to divide by
is
x
it
power
mod 2?
n plus 1, yeah, this will not give you the remainder 0, but the remainder, if you divide by x power n plus 1, will give you one polynomial which is also a part of the code word.
Left
Okay,
shifted.
yeah, left shifted code word.
Okay, so
Okay, yeah. So that justifies whatever we have done so far. Okay, okay, right. So with that, we can choose randomly any of one of these polynomials. So let us say that, let us pick g of x as anything, can take any of these. So if I take x power 3 x square plus 1 as the generator polynomial, as generator polynomial. Okay, so that we should have, to construct the code word table, we should also know have the knowledge of the incoming data as well. So we'll have to assume something for data vector. Assume the vector d, the row vector, as something like 1 0 1 0. Okay, so that's which can be represented as a polynomial as well. So d of x in this case, say 0, 1, 2, 3. So this will be x power 3, 0 times x square plus 1 times x. This would be the polynomial which represents the given data vector. Okay, so therefore we know that c of x, the code word, is nothing but the product of the data vector and the generator polynomial. So this would simply give us d of x is x cube plus x. G of x we have picked from uh, the options that x cube plus x square plus 1. So multiplication of these two polynomials with, remember, with modulo 2 additions. So x power 3 times x power 3 is x power 6 plus x power 5 plus x cube. I'll just take all the terms in the product. So next term is x power 4 x cubed plus x. Okay, as you know, addition of two terms would result in 0, and this would give me simply x power 6 x power 5 plus x power 4 plus x as a code word. Okay, so this implies that the code polynomial or the code row vector of our 0 1 0 1 0 data vector would be, if I start with x power 6, this is 1, x power 5, x power 4, x power 3 is not there, x power 2 is not there, x power 1 is also not there. Sorry, x power 1 exists and x power 0 is not there. Okay, so that's how you can try to construct this. Obviously the length of the code word is 7 because the 7 for 7 comma 4 cyclic code. Okay, so this is for this data vector. So similarly you can extend the same for any other data vector, because there are 2 power k combinations. As I told, there will be 16 possible data vector that is possible. So you can take just one more case with all ones. Okay, for d as 1 1 1 1. Okay, d of x is x cubed x squared x and plus 1. Okay, in this case c of x would be product of d of x and g of x. So try to multiply these two polynomials, x square plus x plus 1 times g of x that you have taken is x cube x square 1. Okay, and this would result in 12 products. So carefully writing what doesn't get cancelled. So this x power 6, and there are two x power 5s, so I would not get x power 5s. X power 4, I will get two x power 4s, even that will not result in the resultant of these two products. How about x cubed? X cubed into 1 is x cubed. Yeah, they think that would result in another x cube as well. So 5 4 3, but the powers of x will exist or not. Anyway, I'll try to multiply and try to simplify later. X power 6 x power 5 plus x cubed, then x power 5 x power 4 plus x square plus x power 4 plus x cubed plus x, then last term as x cubed plus x square plus 1. Okay, x power 5 is there, I can cancel. X power 4 gets also cancelled. Oh, there are 3 x power 3s, and hence only 2 x power 3s gets cancelled, and x power 2 is not, there are 2 here, so this would be simply, the resultant of this would be x power 6 plus, there are no power other than 3, x power 3 plus x plus 1. Okay, so therefore this code word would be 1 0 0 5 and 4, 3 is 1, 2 is 0, x power 1 is there, x power 0 is also there. So similarly we can construct for any of the data table. So what we have done here is I have D and have C. We have done for two cases, 1 0 1 0 and all ones. So this would give us the code word for all ones. This is 1 0 0 1 0 1 1, and for other case we have got 1 1 0 0 and 1 0 0 and 1 0, and hence you can construct this code table for all other 14 combinations. Okay, so that is one of the simplest examples that is possible to generate cyclic code. So if you pick any of the code words in the encoding table, as I said, the cyclically shifted of any code word will also exist in the encoding table, and hence is the property of this cyclic code. Although this is, as I told, this is very crude method of finding out the encoding table. There is definitely a neat method in form of systematic cyclic codes, which I'll pick up in the next session.